just like we have identified usual and unusual values before, we want to do the same thing with probability distributions. We want to use our probability distribution to say which values we would consider usual and which values we would consider unusual or shocking. Now, help me remember this real quickly. Our definitions of unusual so far are outside how many standard deviations of the mean? Huh? 2. Yes, I just didn't hear you. Outside 2 standard deviations of the mean, that means the same thing as what about z-scores? What z-scores are unusual? Anything less than -2 or greater than +2. All right, good. You remember what's usual and unusual. And we have found the maximum usual and the minimum usual before. We just have the symbols for population here. The max usual is the mean plus 2 standard deviations. The min usual is the mean minus 2 standard deviations. Anything between those two numbers would be considered usual. Anything outside those two numbers would be considered unusual. So, we have a probability distribution for a pea hybridization experiment. Who's the father of genetics? I'll go tell Miss Fields and she'll be so happy. Yes. I haven't heard it pronounced that way. You could be absolutely right. I've always said Mendel, but we would spell it the same. All right. Probably whether you're from Tennessee or Alabama. No, Tennessee or Alabama is what I'm going to blame it on. Gregor Mendel, father of genetics, did conduct a lot of experiments on hybridizing peas and studying the genetic effects of mixing genes from different peas. That was his whole life, hybridizing peas. And every morning he would go out to the garden and randomly grab 8 peas and then answer the question, how many of these peas have green pods? That was the question for, 10 years or something. Out of these 8 peas that I grabbed this morning, how many of them had green pods? What are the reasonable answers to that question? 0 through 8. It wouldn't make sense to say I have -2 green pods or I have 10 green pods if I only picked 8. So 0 through 8 are your total possible outcomes. And according to Gregor Mendel's research, here are the probabilities for each of those outcomes. Would you be shocked if you went out in the garden with Gregor Mendel some morning and grabbed 8 peas and none of them had green pods? Would that be shocking? That's unheard of. Not impossible, but highly, highly unlikely. It's highly unlikely that only one of them would have green pods. What is the most common answer to the question, how many green peas did I get this morning? Looking at that probability, 6 had a higher probability than anything else. So, about 31% of the time when he grabbed 8 peas, 6 of them had green pods. Now, what 2 things have to be true in order for me to say, yes, this is a probability distribution? The sum of all these probabilities has to be 1. What other thing? Each individual one has to be a number between 0 and 1. And that's true, so this is a probability distribution. It's true because I've already added them up and I know they equal 1. All right, enter these on your calculator as list 1 and list 2. We're going to find the mean and the standard deviation just like we did for the other problem. I'm going to let you punch that, and I'm not going to this time. I'm going to play like my math lab and tell you what to round to. Since the number of green peas is always a whole number, let's round our mean and standard deviation to the nearest tenth. That's what we've usually done. We've rounded our mean and standard deviation to 1 decimal place more than the original data. So what are you getting for mu? Well, folks still typing. It's okay. List 1, list 2, stat, calc, 1 variable stats. 6 even? Exactly? 6.0. Okay, cool. That's just looking at the table. That's what we said we should expect more times than anything else, because that's the value that had the highest probability. If Gregor Mendel goes out, grabs 8 peas every day for 10 years, then he should expect the answer to how many of these have green pods to be 6. That doesn't mean it will be every time, but that's the average of all the answers to that question. What about standard deviation? What do you get for it? 1.2? Okay, and if we're going to round to 1 decimal place, it would be 1.2. So we can use the range rule of thumb to identify the maximum usual number, what he would not be shocked about, and the minimum usual number, and we could give a range of values that we would consider not shocking. Well, the minimum usual is always the mean minus 2 standard deviations, and the maximum usual is always the mean plus 2 standard deviations. So the minimum usual value would be 6 minus 2 1.2s, or 6 minus 2.4, or 3.6. And the maximum usual would be 6 plus 2 standard deviations, 8.4. So I'm trying to answer this question, identify a range of values that we would consider usual. What would you give for that range of values? No, this is our minimum usual, and this is our maximum usual. Yes, we're considering what's usual. Anything between those two values. That's what minimum usual means, the lowest non-shocking number and the highest non-shocking number. So our non-shocking range would be between 3.6 and 8.4, except, tell me this, if you walked out to the garden with Gregor Mendel one day, grabbed 8 peas, and said, how many of these have green pods? Would you be shocked if there were 8.4? Why? Because you only picked 8 peas. You can't have 8.4 green pods if you only picked 8 peas. So there have been other times where we had to go, well, that's what the formula says, but maybe in some circumstances a negative wouldn't make sense. In this problem, 8.4 doesn't make sense because you cannot possibly get 8.4 green pods out of 8 peas. So I would list that range as from 3.6 to 8. because you can't get 8.4. Now, technically, you can't get 3.6, but this is an average, and you could get that for an average. Miss Ashley? Don't say that something that cannot possibly happen is non-shocking. By definition of can't possibly happen, it would be shocking if it did. So, correct. Correct. And that's not going to happen 99 times out of 100. Just on this particular problem, you should always be thinking about what these numbers mean, not just this is what my calculator said, but if you're thinking about what that means, that can't be usual because it's not even possible. All right. This is one of the most confusing things on test, where are we? Test 2. So whenever I see that, I expect to see red ink pens whipping out and highlighters whipping out and somebody writing That's what I do when a teacher says, this is confusing. You're going to have to work on this. And see, I'm setting a trap for you right now. After you've highlighted this and put a star by it and written important and study, on the practice test when you say, I can't get this unusually high problem right, I'm going to say, go back to that slide that you highlighted and put a star by and a couple of exclamation points and read it again. Any problem that says unusually high or unusually low, this is what you need to be looking at. X successes among N trials is unusually high if the probability of X or more of those things is less than 0.05. In other words, we have a new definition for unusual. We're going to consider unusual anything that has a probability of less than 0.05. Really, that's not new, though, because we already knew that what percent of the population lies within 2 standard deviations of the norm? Of the mean, I mean? 95. So what percent lie outside that? 5% written as a decimal is 0.05. So anything that has a probability of less than 0.05, that's just another way of saying anything outside 2 standard deviations of the mean. But the kicker is remembering that this is not just the probability of X is less than 0.05, it's the probability of X or more. If we're talking about is 5 out of 9 babies with green eyes unusually high, you wouldn't just look at the probability of 5, you'd look at the probability of 5 plus 6 plus 7 plus 8 plus 9. You got to add up some probabilities to answer these questions about unusually high or unusually low. I think I've said this, but just in case I haven't, have I told you you get to use a note card on the test from now on? And you were going to remind me if I forgot, right? A 3x5 card, not a poster, not a piece of paper, not a 4x6, a 3x5. You bring a 4x6, I'm going to take my scissors to it and whittle it down to size for you. 3x5, front and back, microscopic writing, anything you want on there you can bring with you. Because what's important here is not that you memorize a bunch of stuff, but you already have enough vocabulary that if you forgot what a frequency distribution is, but you remembered the words, You could always Google it, right? You don't have to memorize everything on the internet. You just have to have enough words to describe what you're looking for so that you can find the answer online. And that's why I don't mind you having a card. You don't need to memorize a whole bunch more stuff. If you don't understand this pretty well, a whole poster wouldn't help you front and back. If you don't understand it, all the scribble in the world is not going to help you. So you work just as hard to understand. I'm just saying you don't have to memorize. So on my 3x5 card, I would have unusually high probability of X or more is less than 0.05. And I would have unusually low probability of X or fewer is less than 0.05. Here's the problem that gets folks on the homework and gets them on the practice test and gets them on the test. And they all go back to this slide we just highlighted all over. This is the Gregor-Mendel probability distribution that we had a couple slides back. It gives the probability of X out of 8 peas being green peas. And so we want to find the probability of getting exactly 3 peas with green pods. We can read that straight off of the table. Here's 3 out of 8, and the probability of exactly 3 is 0.023. And then we want to find the probability of getting 3 or more peas with green pods. Now I'm going to be sneaky about this. If I wanted 3 or more, that includes 3. And so I could add up these probabilities for 3, 4, 5, 6, or 7. Oh, I'm sorry, I just realized I'm writing off the slide. This is the probability for 3 or more green pods, and I could add those up. I'd have to grab my calculator, enter them all, or I can think about what I learned in chapter 4. The probability of 3 or more is the complement of less than 3. So instead of adding up these 6 numbers, I could just add these 3 numbers and subtract them from 1. The probability of less than 3 green pods is just 0.004. So the probability of 3 or more green pods is 1 minus 0.004. And that's 0.996. It was a lot easier to find the complement of less than 3 than it would have been to add up these 8 probabilities for 3 or more. According to the previous slide, which probability is relevant for determining whether 3 is an unusually high number of peas with green pods? Does the previous slide say to find if 3 is unusually high, you find the probability of exactly 3? Or does it say you find the probability of 3 or more? If you look back at that, it says the probability, or X is an unusually high number of peas with green pods if the probability of 3 or more is less than 0.05. Well, the probability of 3 or more is 0.996, and that is not less than 0.05. So, no, 3 is not an unusually high number of peas with green pods because the probability of 3 or more is greater than 0.05. It's much bigger than 0.05. So 3 is not an unusually high number of peas with green pods. You can see from this example why it's important to understand the previous slide. Um, if you use the probability of exactly 3 peas with green pods, that is less than 0.05. So you would end up saying, yes, it's unusually high. But that's not what you should be using to determine if 3 is an unusually high number of peas with green pods. You should be using the probability of 3 or more, and that's not less than 0.05. So 3 is not an unusually high number of peas with green pods.